Hello and welcome. I'm Michelle Sainer. Today I'm talking about different classifications of different forms of matter. So by the end of this video, you should be able to identify between mixtures, compounds, and elements. So let's first start by defining some of the terms that we're working with today. An element is defined as a pure substance that cannot be broken down into anything simpler. Basically, we're talking about pure silver, pure oxygen, pure hydrogen. So most of these pure substances, these elements, are just simply that. They're just a collection of like atoms. A pure substance that cannot be broken down into simpler, smaller, stable substances. So typically you're looking at things with a chemical formula that contain only one type of atom. For example, you might have gold, hydrogen gas. Even though there are two atoms of hydrogen in a molecule of hydrogen gas, it's considered a pure element because it's the same type of atom, and you can't break it apart without it becoming unstable. You could have pure carbon, or you could have something like chlorine gas, etc. So anytime you're looking at a material that is made up of only one type of atom, it's safe to say that it's an element. Next, we have something called a compound. Now, a compound is a substance that it can be broken down into smaller or simpler substances made of two or more types of atoms that can be broken down into simpler, smaller substances. Compounds are typically made when you have two or more types of atoms bonded together. Some examples of a compound could be like water, H2O. You have two atoms of hydrogen, one atom of oxygen. They're bonded together, but they could be broken down into simpler, smaller pieces. You could just have oxygen, or you could just have hydrogen. So compounds are typically, we're looking at things that are on the molecular level. Finally, we will have mixtures. Mixtures are blends of two or more kinds of matter. And although they're blended together, they each retain their original properties and identity. We have a couple of different examples of mixtures. If you have a mixture that is uniform in composition, that is to say it's the same throughout, we call this homogeneous. If it is not the uniform throughout, if it's got kind of like areas that are a little bit different in one phase or another, one stage or another, we call these heterogeneous. And if you have a mixture that is a homogeneous liquid, we call those solutions. So a substance dissolved in water or dissolved in some other liquid is called a solution, and that's another type of mixture. There are some properties that pure substances have. Pure substances are fixed in their composition. Every sample of a pure substance has the same characteristic properties throughout. Every sample has uniform composition. The only way to separate a pure substance is through some sort of chemical change. And chemical change, an example that is the breaking and forming of bonds. So the only way to separate a pure substance is by breaking bonds. Mixtures, on the other hand, can be separated physically. So what that means is you could pour off a little bit of the mixture, you could sort solid mixtures that are solids, you could filter them, and they could be boiled off, for example. Mixtures can be separated physically. You don't have to undergo any sort of chemical change to separate a mixture. So in this example, no chemical bonds are broken or formed. And we will see an example of this a little bit later in the lab. So let's just compare very briefly chemical versus physical changes. So we'll look at chemical properties, we'll look at chemical changes, and we'll compare them to physical properties and physical changes in this little table here. So chemical properties relate to a substance's ability to undergo changes to transform into a different substance. To undergo changes that transform it to a different substance. So an example of a chemical change is a chemical reaction. Remember, we can abbreviate a reaction RXN. And this is a change in which one or more substances are converted into different substances. A change in which one or more substances are converted into different substances. Let's compare that to physical changes. Physical changes are ones in which the phase is changing. I like to think about boiling water as a perfect example of a physical change. You have liquid water, you apply heat to it, you excite those molecules kinetically, and eventually you have a phase change into gas water. The molecules themselves remain intact. We're still talking about H2O. We're just talking about H2O in its liquid versus its gas form. So this is a prime example of a physical change. So a physical change is a change in the substance that does not involve a change in identity. And a great example of this is it can include a phase change, like our water example going from liquid to a gas. So our big differences here, Chemical reactions change the nature of the subject, substance, change the identity of a substance into a new substance, a new molecule, whereas physical changes are typically not changing, or definitely not changing the identity of those substances, but maybe just the phase or the way that those atoms are spaced out, atoms and molecules are spaced out. So a physical property is a characteristic that can be observed or measured without changing the identity of that substance. Okay, so how do we tell? How are we able to differentiate between elements, compounds, mixtures? We are going to use this flow chart to decide. So this flow chart comes from our text here. Starting at the top, we're talking about matter. We first ask ourselves, can it be physically separated? If yes, it can be physically separated by boiling, by sorting, by separating in some manner, then we're talking about something that is a mixture. If the mixture is uniform in composition, it's a homogeneous mixture, meaning same throughout. If it's not uniform in composition, then we're talking about a heterogeneous mixture or different throughout. So granite, wood, or blood would be examples of heterogeneous mixtures. They're not exactly the same in every single spot, unlike our air or sugar dissolved in water or stainless steel, which are uniform throughout. Those are homogeneous mixtures. Back to the top, if you cannot separate a substance with physical means, then you are probably talking about a pure substance. So pure substance, is it a compound or is it an element? Well, if you can decompose it, that is to say, break it apart by chemical means, the breaking of bonds and undergoing some sort of chemical reaction, then we're talking about a compound. Two or more different types of atoms bonded together, like H2O, or sodium chloride, NaCl, or sucrose, a sugar molecule. If you cannot break these things apart into smaller, simpler substances, and you only have one type of atom in this pure substance, then you're talking about an element like gold, aluminum, oxygen, or chlorine. And remember, you can have something like oxygen where two atoms of oxygen are bonded together and it's still considered elemental oxygen. And that's because oxygen just isn't stable by itself with one atom. Same thing with chlorine. Chlorine gas is stable with two atoms of chlorine. So take a look at when you are deciding between compounds and elements, take a look at how many different types of atoms are in that chemical formula. If you have one type of atom, it's going to be an element. If you have a couple different types of atoms, you're going to be talking about a compound. So next, I would like to take you in my lab and show you a few examples of different mixtures, elements, pure substances, and compounds. So I'll see you there.
All right, welcome to my lab. We are going to look at 4 different substances. So write down these substances and you can help me identify whether these are mixtures, either homogeneous or heterogeneous, compounds, or pure substances. So I'm going to put my lab glasses on and share my camera with you. So let's start with copper sulfate, CuSO4. I can already tell from the description of this where I have multiple different types of atoms, copper, sulfur, oxygen. I have multiple different types of atoms, so I know that this is not a pure substance. Here is what it looks like. I've got these lovely blue crystals here. They're solid. By itself right now, I would say that this is a compound, so 2 or more different types of atoms bonded together. But what happens when I put it in the water? Stir it up so it's a little bit more uniform throughout. As it begins to dissolve, something changes here. Something changes. It goes from being a compound, just something that the copper sulfate on its own, now it's mixed together in a different substance, water. And that mixing should give you like a little indication that we're talking about a mixture. When we decide whether it's homogeneous or heterogeneous, what we're looking is for uniformity. So if you look at this substance, you can see it's uniform throughout. There's no part that contains, more or less copper sulfate, more or less water. It's all pretty much uniform throughout. It's completely dissolved through. So when you have a solid like this dissolved in water, it's called an aqueous solution. So this is an example of a mixture that is now a solution. That is to say, heterogeneous or homogeneous throughout, the same throughout. All right, let's look at our next example. Now we're going to see sand in water. So I've got two different substances, sand and water. You can kind of see the sand there settled at the bottom of this beaker of water. I have to decide what type of substance this is. It's not a pure element because I can very clearly see two distinct things happening. I could see the sand and I could see the water. So it must be some sort of mixture. Remember that pure mixtures are either homogeneous or heterogeneous, so we're looking for it to be uniform throughout. So I can see that on the bottom, it's definitely a lot more sandy, and on the top, it's definitely like a lot more liquidy. So this is not a uniform mixture, right? This is different throughout. So this is an example of a heterogeneous mixture. What I'd like to do with this mixture is show you a little bit about how you can separate mixtures physically using physical means. When I go to separate the water from this sand, which I'm going to do right here, I can pour off as much water as possible. That's called decanting. So I've just decanted the water, the sandy water there. And I've almost separated it completely from the sand. But I can use another physical process to continue separating this out. I'm going to go ahead and put this on a boiler plate and turn up the heat, and I'm going to boil out the water. We'll come back to that a little bit later and see if we can get the sand isolated just purely by physical means. And while we're doing that, I'm going to move on to our next example. So here I have a sodium chloride, good old table salt, and water. Sodium chloride, chemical formula NaCl. You can tell with two different atoms that this is going to be a compound as opposed to a pure element. And I'm going to go ahead and dump it into my water, stir it up till it all dissolves, because I'm trying to make this mixture of two or more substances uniform, trying to make this a heterogeneous mixture. Now, if I can do that, if I can get it all completely dissolved, then I will have myself another aqueous solution. That is to say, something dissolved in a liquid that is homogeneous in nature is a solution. So there's an example, there's your NaCl in water. Let's look at one more example, and this one's kind of a fun one. So in this example, I have a beaker and it's full. Let's see if I can get a good shot of that for you. It's full of iron filings and sulfur. So this is iron inside of sulfur. You can see it doesn't look the same throughout. I've got some chunks of iron in there, some chunks of sulfur. So again, this mixture is heterogeneous in nature. It is not uniform throughout. And another example of a way that I can separate substances, separate mixtures by physical means is here in the iron. Let's see if I can get a little bit closer. You could see that I've got iron filings. I'm using a magnet to separate them out from the sulfur there. And if I were to keep doing that, I could probably tap all the sulfur off and pull those irons right out of this mixture. Here, let me see if I can show you on the bottom. There it goes, up around the side. So magnets are another way that I can physically separate metal from other substances. All right, so it's been a few minutes and my water continues to boil away from my sand. I'm trying to isolate this again through physical means and show you that mixtures can be separated without breaking or forming any bonds. So you can see my vessel here is getting quite hot. I'm burning off quite a bit of water into steam here. You can see the condensation forming on the inside. So we'll give it a few more minutes and see if we can't completely separate this mixture by this physical means of boiling. Oh boy, it's really going now. I can see quite a bit of steam coming off. The bottom of the vessel is really starting to dry out. There's only a tiny bit of liquid left in here. And this idea of boiling off one substance that has a lower boiling point than another is one of the ways that we most often separate substances in the lab. So as we watch it continue to steam away, You'll be able to see all of the water eventually leave this vessel, this little beaker here, and all that we'll be left with is the sand. All right, at this point, I have almost completely boiled all of the water away. My beaker's very hot, so I'm not going to touch it. Hot glass and cold glass look exactly the same, so don't take any chances. And you can see that pretty much all I'm left with here is just hard, compact sand at the very bottom of the vessel. So I was able to use a physical means of separating the water and the sand. This is really important for identifying mixtures. The next time we see each other, we're going to do a little bit more practice around identifying substances as pure substances, compounds, heterogeneous or homogeneous mixtures. So we do that by making observations, but more importantly, we'll be looking at the chemical formula. All right, thanks for joining me, and I will see you next time. Have a great day.